An electrolyte, ladies and gentlemen. We talked about the different types of solutions yesterday. A solid dissolved in a solid, a liquid dissolved in a solid, for instance. We didn't get a chance to talk about an electrolyte. An electrolyte is simply a substance that dissolves in water to give a solution that conducts electricity. Conducts an electricity. So, how would I know whether something conducts electricity? I have a little wire harness. I have them up here. Let me see if I can find one. Yeah, here they are. What I do is I just take a little wire harness, as so, which is kind of what they're saying here. And if I put each lead into the liquid and the light lights up, then I'd say, yeah, that conducts electricity. But if I would put it in there and it doesn't light up, I'd say, ooh, that's a non-electrolyte. It will not conduct electricity. Okay? So if we have time later on in the period when we get done with the notes, I'll run through a couple of demos here with electrolytes there. But as you can see right here, we have a positive terminal. Okay? What is positive color-wise? Red. What is negative color-wise? Black. Okay, remember that, those of you that drive cars, if you need to jump your car. It's nice to know. If you don't know that, don't be jumping your car. Let someone else do it. Huh? Red go to black? I don't know what would happen, really. I mean, it wouldn't work. But, you know, red to red. Okay? You put the red on red and the black on black. That's the way that the charge runs. Actually, the charge runs, the negatives will come over here and then go to the positive and then go all the way around the circuit. It's the electrons that are flowing. Okay? Right. Same color, same color. Just like when you're hooking up like a VCR or a DVD player, you don't put red with yellow, do you? Right. You're not going to get it to work. A non-electrolyte then simply is something that does not conduct electric current. So right here I got my circuit and my light bulb is not lit up. So just a very simple test that I can put my wire harness, and when I put the two different leads into the liquid, if it lights up, it's an electrolyte. If it doesn't light up, it's a non-electrolyte. Right here, I'm just trying to show you, and it might be a little hard to see, but it's just another picture. But the point being, this one is a non-electrolyte. See my light? I got nothing right there. This one is a weak electrolyte. This one is a strong one. How can you tell the difference? The brightness of the light bulb. So that will give you a ballpark, okay? A ballpark, it will give you a qualitative value. It won't give you a quantitative. You don't know how conductive. It's not giving you a number, but you're saying, ooh, that's a little bit brighter than the other one, so it conducts electricity a little bit better. It's a stronger electrolyte than my other one, which was a weaker one. Now, we're going to do a lab tomorrow. Okay, we're going to do a lab tomorrow, so don't forget to watch your pre-lab video. Okay, you'll have a pre-lab video of a Google Classroom. It should have went active today at about 7:25. Okay, so there's a pre-lab video that you need to watch. We'll do a lab about factors affecting the rate of dissolving. What are some factors? Increasing the surface area, agitating the solution, and finally, heating the solvent. Those three things are factors that affect the rate of dissolving. Let's talk a little bit about each one of these individually. Increasing the surface area. Okay, I've got 2 blocks there. All right, I've got 2 blocks there. And when we talk about increasing the surface area, we're talking about the surface to volume ratio. Okay? The surface to volume ratio. If I look right here, what is my surface to volume ratio right here? 6 to 1, right? What is my surface to volume ratio here? 3 to 1. So which has the better surface to volume ratio? Which has the better surface to volume ratio? The better one? Which one has a higher surface to volume? This one, right? 6 to 1 is higher than 3 to 1, right? Would we agree? So my surface to volume ratio right here is higher than my surface to volume ratio here. Even though that this appears like it's going to have a bigger surface area, right, to volume. Stop and think about this. That little particle in the middle of this square, all right? That one little particle in the middle of the square, which is the water that dissolves this sugar cube here? Where's it going to get to quicker? The one in the middle of this square or the one in the middle of this square? Okay? It's going to take longer because it's got to go through a lot more area to get to the middle of this one than it does to get to the middle of that one, doesn't it? See what I'm trying to say? Okay? So, the surface area is increased as we get things littler. Okay? Could I crush this up to be this size? Yeah. So then they would dissolve the same. And you're going to see this in a lab tomorrow. You're going to see this. Okay? We're going to take rock salt, which would be a simulation of the big block, and just regular salt. And you're going to see which one dissolves faster. Agitating. Which one's going to dissolve faster? A, right? Okay? A is going to dissolve faster because of why? I'm stirring, but what's that got to do with it? We're getting those particles in there moving around faster, right? Are the particles moving around at all in B? No. No. Does it matter if I shake it or if I stir it? No, I'm still getting that movement, right? I'm still getting that movement. Heating the solvent. Right here is what we call a solubility curve. All right? A solubility curve. And what we have is all of these lines are different substances. For instance, if I look at this line going up right here, KNO3, that's potassium nitrate. So as I heat potassium nitrate, it becomes a great deal more soluble than at lower temperatures. Okay? Right here, this line that starts right here and goes all the way across right there, that's sodium chloride. That's salt. Okay? That's salt. Now, if you look at this, does everything increase solubility as we heat it? No, does not. Here's SO2. Sulfur dioxide decreases. Okay? Right here's ammonia. That line. Hydrochloric acid is that line. Okay? A lot of the times, gases, I would say probably most of the time, gases, when we increase temperature, the gases are less soluble in water. So we've got solubility curves. Well, what is solubility? What is solubility? The solubility is the amount of a substance required to form a saturated solution with a specific amount of solvent at a specified temperature. The amount of the substance required to form a saturated solution with a specific amount of solvent at a specified temperature. So in order to have a solubility, I need to have three things. I need to have three things in order to determine a solubility. Can you see what they are? What's one of the things I need? A specific amount of solvent. What else? A specific temperature. And the third one is? A specific amount of? What are we missing? We've got solvent. We've got temperature. What else do we need for a solution? The solute, right? So when we're looking at this solubility here, you're going to see something like this. And my three things are all in different colors. At 20 degrees Celsius, I can dissolve 87 grams of sodium nitrate per 100 grams of water. That is a solubility. Let me ask you this. How much could I dissolve if I had 200 grams of water? Double it, right? What if I only had 50 grams of water? Half of it. Okay, so we could vary that in different amounts. You'll have to do that on WebAssign. A saturated solution is a solution that has the maximum amount of dissolved solute. I cannot dissolve any more material. I cannot dissolve any more solute into that solution. I have the maximum amount. Here is the solubility of sodium chloride at 20 degrees Celsius in 100 grams of water. So I have 35.9 grams of sodium chloride. Could I dissolve at 20 degrees Celsius 100 grams of water? Could I dissolve 40 grams of sodium chloride? Could I? No. I could not, because I could only dissolve how much? 35.9. What if I would put 40 grams in there? 35.9 grams would dissolve, right? How much would be laying at the bottom of my beaker then? 4.1, the leftover. Okay, couldn't dissolve it all. An unsaturated solution is a solution that contains less solute than a saturated solution under the existing conditions. So we just said, let's look at again at that 20 degrees Celsius mark. We said on the last slide that what was the saturation point? When did I have a saturated solution? 35.9. Here I'm at 20 degrees Celsius. I still have 100 grams of water, but I only have 25.9 grams. So could I dissolve more salt? Could I dissolve more salt into that situation there? You could tell me how much, right? How much more salt could I dissolve there? 10 more grams. So I could still dissolve more into this solution. So that is what we call an unsaturated solution. Now here's the mind blower. A super saturated solution. I'll give you a little time here to write this down. Okay, a supersaturated solution is a solution that contains more dissolved solute than a saturated solution contains under the same conditions. What's wrong with that statement? Anybody see what's wrong with that statement? What's a saturated solution? Saturated has maximum amount, but yet the supersaturated has more? How can you have more than the maximum? That's the problem, right? How can you have more than the maximum? Okay, what happens here, folks? What happens is we take the solution, okay? We take the solution and we heat it up. As it heats up, we can dissolve more material there. We can dissolve more material as it heats up. And then what we do, we just simply take the heat off of it. What's eventually going to happen to that solution? It's going to cool down, isn't it? When it cools down, that material stays in solution. So we actually have more than we should have in that solution. That leads us to the bottom part there. A supersaturated solution may remain unchanged for a long time if you don't disturb it. But once that's disturbed, all of the extra solute that is dissolved will come out of solution. Okay? It will come out of solution. Now look at right here. Okay? I don't know if it's necessary to write these down, but at 100 degrees Celsius, I can dissolve 39.2 grams of salt per 100 grams of water. At 20, I can only do 35.9. So if I heat this up to 100, and I have 35.9 in there, right? Then I cool it to 20. That 35 or 39.2 will stay in solution. It'll stay there. So actually, I'll have the difference of those two will be what I have more than should be allowed to be in there. Now here's a video. Okay? Here's a video. I'm going to pause it here for a second because I don't think that my volume's on. Oh, well, I guess I shouldn't have paused it. Hi, Grandma. We're going to watch about Pete here until I can skip the... Oh, I can skip it. Now, this solution is super saturated. Okay? So basically what we have here is we have a solution that's already been super saturated. He's dissolved more in there at a higher temperature, and he said it's been sitting there all year. So he's just let it sit there. He had the cover on it so it went undisturbed. Now what happens when he puts this one crystal into the supersaturated solution? I don't think these people get out much. Now that is the crystals coming out of solution. That's how much more was dissolved in there than what was at the saturated point. Looks pretty cool, doesn't it? Right, he put in, it could be as little as 1 grain of the substance to just disrupt equilibrium. Now watch this. That liquid solution, it's warm. Well, what was happening there? If it's warm, heat must be released, given off. So now we don't any longer have that liquid solution, do we? It's now a solid. Now I don't even want to talk about all of the violations that they had there with right, they didn't have goggles. Okay? Number one, they didn't have goggles. We had a dress code violation with that little spaghetti or whatever. Well, I guess that wasn't a spaghetti scrap, but yeah, definite dress code violation. No goggles. Had her cell phone out, right? I'd have snatched that up. Well, yeah, but it wouldn't have been so fun if somebody got a chemical in their eye, would it? Yep. Thermal pollution. The solubility of gases is greater in cold water than in hot water. I just told you that gases, as we increase the heat, become less soluble. Less soluble as we increase the heat. So, think about it. If I have higher water temperatures, how's that going to affect the amount of oxygen dissolved in it? Water temperatures are up. What about the oxygen dissolved in it? It'll be lower. It'll go down. Okay? So if we have this thermal pollution, if we have hot water, it's going to have less oxygen. Do you think having less oxygen in a lake would harm the aquatic animal life? Yeah. Yeah. Most definitely. I've seen around on Grand Lake during the summers, if we have very little rain, and hot temperatures during the summer, we don't have as much oxygen dissolved in the lake. And at times, some of the junkier fish, and what I mean by junky fish are like shad, okay? At times, there'll be not enough oxygen in the water for the shad to live, and they'll literally suffocate. And then they'll start floating. Solute solvent interactions. Solute solvent interactions, a general term to remember is like dissolves like. Like dissolves like. That's a rough but useful rule for predicting whether one substance will dissolve another. Like dissolve like depends on the type of bonding, the polarity versus the non-polarity, and the intermolecular forces. So, like dissolves like. Food coloring and water. What do you think? Do you think food coloring and water are alike? Just because they're both liquids doesn't matter? Will food coloring dissolve in water? Will that spread out evenly there? Yeah. So food color and water are like, okay, like and like. What about oil and water? They're not alike, are they? So if I put oil in water, it's going to look something like that, correct? Where I have my oil layered at the top and my water at the bottom. Why is the oil at the top? Less dense than water. The higher density will sink, the lower density will float. So that oil is actually floating on top of that water there. So oil and water are not alike. Oh, sure. Sure, there's things that are less dense than oil. Yeah. We could layer it all out. Immiscible. Oil and water are immiscible liquids. Oil and water are immiscible liquids. Well, what's an immiscible liquid? It's where the solutes and the solvents are not soluble. I cannot dissolve oil in water, can I? So they are immiscible liquids. However, could I dissolve food coloring in water? Yes, so they are miscible. And miscible liquids are ones that dissolve freely in one another. One of my favorite answers to a question I got, of course I marked it wrong, but the question on the quiz was, define immiscible. And the student put, immiscible is the opposite of miscible. And I said, although a correct statement, that doesn't really tell me that you know what immiscible is. All right. Okay, we're going to stop there. We didn't quite get where I wanted, but that's okay. We're close. Now, make